And now in this lecture we'll answer on two questions. In the first question we'll find out the radius of this circle, and in the second question we'll find out the area of this circle using two different methods. So we'll start with the first question. In the drawing we have a circle, and this is the right angle ABC. This is angle ABC, that is the right angle. Side AB equals to 3 units in its length. Line segment AD equals to also 3 units in its length. Line segment DC equals to 1 unit in its length. Point O is the center of this circle. Again, our task is to find out the radius of this circle. So here we can implement rule 25. Okay, rule 25. If from a common external point, point P, you will draw a tangent. From point P we have tangent PA to a circle and a line segment that cuts the circle in 2 points, B and C. From the same common external point P we also second PC that cuts the circle in 2 points, B and C. So in this drawing, the following equation is true, that PA square equals to PB times PC. Again, PA square equals to PB times PC. So we can actually implement rule 25 in our drawing. In our drawing, if we focus on this common external point, point C, from this common external point, point C, we have tangent CE. Tangent CE is tangent to this circle at point E, and we also second CA that cuts the circle in 2 points, D and A. So all the requirements for full 25 are satisfied, and therefore we can implement rule 25. So I write it down. So if you focus on the common external point, point C, according to rule 25, the following equation will be true. That CE square equals to CD times CA. Again, CE square equals to CD times CA. CE square equals to CD times CA. This equation is the implementation of rule 25 in our drawing. CE is the missing tangent, so we limit the CT, so it is CE square equals to CD. CD is 1 times CA. CA in total is 1 plus 3, that is 4. So according to rule 25, actually found out that CE square equals to 1 times 4. 1 times 4 is 4. So CE square equals to 4. Here we take a root out of this equation. And we get that CE equals to the square root of 4, that is 2. The length of tangent CE is 2 units. So I write it down. This is tangent CE that equals to 2 units in its length. In the next step, we will implement the Pythagoras theorem on this right triangle ABC. According to the Pythagoras theorem, In any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Side AB of the right triangle ABC equals to 3 units in its length. The hypotenuse AC equals to 1 plus 3, that is 4, and BC is the missing side. Here by PT is the abbreviation for Pythagoras theorem. Okay, this is the right triangle ABC, this is the curvature of the original drawing. This right triangle ABC, AC square, that is the square of the hypotenuse, equals to AB square plus BC square. So I write it down. AC square, that is the square of the hypotenuse, equals to AB square plus BC square. AC is 4, therefore AC square is 4 squared, that is 16. And it is equals to AB square. AB is 3, therefore AB square is 3 squared, that is 9, plus BC square. BC is the missing side, so BC is the missing side, so we leave it as it is. So in total we found out that (16) equals to 9 plus BC square. Here we subtract 9 from this equation, and we get that 16 minus 9 is 7, so 7 equals to BC square. Here we take a lot out of this equation, and we get that BC equals to the square root of 7 units in its length. This is side BC, that equals to the square root of 7 units in its length. So what is the length of this 9 segment BE? From the drawing it is very easy to see that BE equals to BC minus EC. So write it down. BE equals to BC minus EC. So BE equals to BC. BC is square root of 7 minus EC. EC is 2. So in total, we found out that BE equals to square root of 7 minus 2 units in its length. This is 9 segment BE. This equals to the square root of 7 minus 2 units in its length. In the next step, we'll join points O and D together by a straight line. It is given us the question that point O is the center of this circle. So point O is the center of the circle, point E is the point of the circle itself. Actually, point E is the point of tendency BC with this circle. So point E is the tangent on the point on the circle. So OE is the radius of this circle. We define the radius of this circle as R. So OE equals to R. The radius OE is equals to R. The radius OE is drawn to point E. That is the point of tendency of tangent BC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius BO. Again, tangent BC will be perpendicular to the radius EO. If BC is perpendicular to EO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to all one. In the next step, we will do another construction. That is to say, from point O, that is the center of this circle, we will draw perpendicular on AB. Again, from point O, we will draw perpendicular on AB. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point O and AB. This point is point L. By doing this construction, we created here quadrilateral LOEB. Inside quadrilateral LOEB, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4 pieces again, in total they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore these 4 pieces again must be equal to 90 degrees in its size. So in quadrilateral LOEB, we have 4 right angles, and therefore according to rule 5, quadrilateral LOEB is rectangle. So already known, quadrilateral LOEB is rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle LOEB, side OE must be equal to the opposite side LB. But OE is R, it is the radius of the circle, therefore the opposite side LB must be also equal to R units in its length. Likewise, according to the same rule, in the same rectangle LOEB, side BE must be equal to the opposite side LO. But BE is square root of 7 minus 2, therefore the opposite side LO must be also equal to the square root of 7 minus 2 units in its length. What is the length of this? This is 97 AL. From the drawings it's very easy to see that AL equals to AB minus LB. Again, AL equals to AB minus LB. So write it down. AL equals to AB minus LB. So AL equals to AB. AB is 3 according to what is given us in the question. Minus LB. LB equals to R. So in total, AL equals to 3 minus R units in its length. AL equals to 3 minus R units. In the next step, we will join points O and A together by set 9. Point O is the center of the circle, point A is the point on the circle itself, therefore OA is the radius of this circle. This is equal to 1. In the next step, I'll copy the right grand triangle ALO in a new page, and we will implement on it the Pythagoras theorem. Side AL equals to 3 minus arguments in its length. Side ALO equals to the square root of 7 minus 3 in its length. And the hypotenuse AO equals to R. It is also the radius of the circle. Here by PT is a abbreviation for Pythagoras theorem. So actually, this is the right triangle ALO, the approach from the original drawing. And this right triangle ALO turned into the Pythagoras theorem. AO square, that is the square of the hypotenuse, equals to AL square plus LO square. So write it down. AO square, that is the square of the hypotenuse, is equal to AL square plus LO square. AO is R, therefore AO square is R square, and it is equal to AL square. AL is 3 minus R, therefore AL square is 3 minus R squared plus LO square. LO equals to the square root of 7 minus 2, therefore LO square is square root of 7 minus 2 squared. So in total we should find out that R square equals to 3 minus R square plus square root of 7 minus 2 squared. So R square equals to 3 minus R squared. 3 minus R squared equals to 3 squared, that is 9, plus R square minus 2 times 3 times R, that is minus 6R, plus square root of 7 minus 2 squared. Square root of 7 minus 2 squared is equal to 0.417. So in total we found out that R square equals to 9 plus R square minus 6R plus 0.417. So here we have R square on both sides of this equation, so R square will get cancelled. I'll take cancelled R square, in this side of the equation we left with nothing, that is to say 0, while on the other side of this equation we have 9 plus 0.417 is 9.417 minus 6R. So in total, if you found out that 0 equals to 9.417 minus 6R. Here we will add 6R to this equation, and we get that 6R equals to 9.417. Here we divide this equation by 6, and we get that the radius R of the circle, that is the radius that we are looking for, is equal to 9.417 over 6. That is actually 1.57 units in its length. So if we again, we found out that the radius of this circle, R, is equal to 1.57 units in its length. So we finish with the first question. In the next step, I will present to you the second question, and we will answer on the second question by using two different methods. So, in the second question, our task is to find out the area of this circle. So, in the drawing we have a circle. This is line segment BC. This is equal to 6 units in its length. This is called BA. That is equal to 13 units in its length. This is line segment CD. That is equal to 18 units in its length. Those two angles, they are both equal to 90 degrees. They are right angles. Again, our task is to find out the area of this circle. Those two right angles are defined as one-sided interior angles. And the sum of those two right angles is of course 180 degrees. And according to rule 27, if the sum of two one-sided interior angles is equal to 180 degrees, then they are located between parallel lines. That is to say, according to rule 27, because of the fact that the sum of those two one-sided interior angles is equal to 180 degrees, they must be located between parallel lines. That is to say, chord BA is parallel to line segment CD according to rule 27. So I write it down. I found out actually that chord BA is parallel to line segment CD according to rule 27. In the next step, we will define the center of this circle. This point is point O. And from the center of this circle, that is to say from point O, we will draw perpendicular on CD. Again from point O, we will draw perpendicular on line segment CD. So actually, this angle equals to 90 degrees, and and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and line segment CD. This point is point M. Here we can implement rule 19. I'll repeat quickly on rule 19. According to rule 19, the perpendicular from the center of a circle towards any chord bisect the chord. Again, the perpendicular from the center of a circle towards any chord bisect the chord. Bisects the chord. So in the drawing we have a circle. Point O is the center of the circle. AB is according this circle. And according to this rule, rule 19, the perpendicular OM bisects chord AB. Again, the perpendicular OM bisects chord AB. That is to say, it divides chord AB into two halves. The first half is AM, the second half is MB, and of course AM equals to MB. So according to rule 19, the perpendicular from the center of the circle towards any chord bisects the chord. So we can actually implement rule 19 in our drawing. In our drawing, from the center of this circle, that is to say from point O, we have actually before that we will extend the perpendicular OM by a straight line until it touches chord BA. Repeat again, we will extend the perpendicular OM by a straight line until it touches chord BA. And we will find the touching point of the extended perpendicular OM with chord BA. This point is point M. According to rule 27, line segment CD is parallel to chord BA. And therefore, the perpendicular OM, or the extended perpendicular OM towards chord BA will be also perpendicular to chord BA. Why? Because of the fact that OM is perpendicular to CD, the extended perpendicular OM must be also perpendicular to chord BA. Why? Because they are parallel to each other. So, therefore, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So it is very simple. If we have two parallel lines, for example, if line A is parallel to line B, line A is parallel to line B, and from this point we will draw perpendicular to line A, and we will extend the perpendicular towards line B. Then the perpendicular to line A will be also perpendicular to line B. Okay. The perpendicular to line A is also perpendicular to line B. From point O we have perpendicular OM to line segment CD, and therefore the perpendicular OM, the extended perpendicular OM, will be also perpendicular to chord BA. Why? Because BA is parallel to CD according to rule 27. Okay, so now we can implement rule 19 in our drawing. Why? Because in our drawing, from the center of this circle, that is to say from point O, we have perpendicular ON on chord BA. Again, from the center of the circle, that is point O, we have perpendicular ON on chord BA. And according to rule 19, the perpendicular from the center of the circle towards any chord bisects the chord. So the perpendicular ON to chord BA bisects chord BA. That is to say, it divides chord BA into two halves. BA in total equals to 13, therefore the first half BN is 13 over 2, that is 6.5, and the second half NA will be also equal to 6.5 units in its turn, according to rule 19. If you focus on the upper quadrangle BCMN, in the upper quadrangle BCMN, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4 pieces again, in total they must be equal to 360 degrees. According to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. And therefore this 4 pieces again must be equal to 90 degrees in its size. So quadrangle BC and F, we have 4 right angles. According to rule 5, quadrangle BC and F is a rectangle. So I write it down, quadrangle BCMN is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle BCNM, side BN must be equal to the opposite side CN. But BN is 6.5, therefore the opposite side CM must be also equal to 6.5 units in its length. ON is perpendicular, so ON is a perpendicular, it is absolutely a straight line. So if you focus on the lower side of the side line ON at point M, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have the lower side of the straight line ON at point M, we have this angle that is a right angle according to our construction, plus this missing angle. In total the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. In the next step we will do another construction, that is to say, from this point A, we will draw perpendicular on CD. Again, from point A, we will draw perpendicular on line 7 CD. So actually, this angle equals to 90 degrees. And this angle also equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point A and line 7 CD. This point is point L. By doing this construction, we can do the lower quadrangle NMLA. Inside the lower quadrangle NMLA, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4 pieces again, in total it must be equal to 360 degrees according to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. And therefore this 4 pieces again must be equal to 90 degrees in its size. So in quadrangle NMLA we have 4 rectangles, and according to rule 5, quadrangle MNLA is a rectangle. So, I wrote it down. Quadrangle MNLA is a rectangle because it has 4 rectangles. But we also know that the opposite sides of a rectangle are equal to each other. So the lower rectangle NMLA, side NA must be equal to the opposite side ML. but NA is 6.5, therefore the opposite side ML must be also equal to 6.5 units in its length. What is the length of this short line segment LD? From the drawing, it is very easy to see that LD equals to CD minus CL. Again, CD minus CL equals to LD. So already know. LD equals to CD minus CL. So LD equals to CD. CD equals to 8 units in its length, according to what is given in the question. Minus CL. CL equals to 6.5 plus 6.5, that is 13. So in total, LD equals to 18 minus 13, that is 5. LD equals to 5 units in its length. In the next step, we will extend line segment DC by third line until it touches the circle. And we will define the touching point with the extended line segment DC with this circle. This point is point T. By doing this construction, we're going to do code TD. This is called TD. So now we can implement all 19 on code TD. Why? Because from the center of this circle, that is to say from point O, we have perpendicular OM on code TD again. From the center of this circle, that is to say from this point O, we have perpendicular OM on code TD. And according to rule 19, the perpendicular from the center of the circle towards any chord bisect the chord. So according to rule 19, perpendicular OM bisect chord TD. If OM bisect chord TD, it means that TM equals to MD. So already know. I should found out that according to rule 19, TM equals to MD. It was perpendicular MD bisect chord TD. But MD in total equals to 6.5 plus 5, that is 11.5. So we can write here that MD equals to 11.5. And for this equation, TM equals to MD equals to 11.5. We know that TM also equals to 11.5 units in its length. From one side, Tm equals to 11.5 units. But from the other side, Tm also equals to Tc plus Tm. Again, Tm equals to Tc plus Tm. So as you know, Tm also equals to Tc plus Tm. And from this equation, 11.5 equals to Tm equals to Tc plus Tm. we will derive that 11.5 equals to TC plus CM. So 11.5 equals to TC plus CM. But we already found out that CM equals to 6.5. Therefore, we substitute CM by 6.5, and we get that 11.5 equals to TC plus 6.5. Here we subtract 6.5 from this equation, and we get that TC equals to 11.5 from 6.5 is 5. So TC equals to 5 units in its length. This is the short line segment TC that equals to 5 units in its length. In the next step, we will extend line segment BC by a straight line until it touches the circle. And we will define the touching point of the extended line segment BC with this circle. This point is point Q. By doing this construction, we created chord BQ. Chord BQ intersects with chord TD at point C. Again, chord BQ intersects with chord TD at point C. So I write it down. Chord BQ intersects with chord TD at point C. So here we can implement rule 15. Whenever two chords intersect with each other, you can implement rule 15. So repeat quickly rule 15. According to rule 15, if chord AB intersects with chord CD at point O, then the following equation is true, that AO times OB equals to CO times OD. So in the domain we have a circle. This is chord AB that intersects with chord CD at point O. Again, chord AB intersects with chord CD at point O. So in this moment, the following equation is true, that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So we can implement rule 15 in our drawing. Why? Because as I already mentioned before, we have in our drawing two chords that intersect with each other. Chord BQ intersects with chord TD at point C. The intersection point occurs at point C. So all the requirements of rule 15 are satisfied, and therefore we can implement the rule 15. According to rule 15, the following equation is true, that TC times CD equals to BC times CQ. Again, TC times CD equals to BC times CQ. So I write it down. TC times CD equals to BC times CQ. And again, according to rule 15, the following equation is true, that TC times CD equals to BC times CQ. This equation is the implementation of rule 15 in our drawing. TC is 5 times CD. CD is 18, according to what was the question. And it is equals to BC. BC is 6, also according to what was the question, times CQ. CQ is the missing line segment, so leave it as it is. So in total, according 415, we found out that 5 times 18 equals to 6 times CQ. Here we will divide this equation by 6, and we get that CQ equals to 18 over 6 is 3, and 3 times 5 is 15. So CQ equals to 15 units in its length. This is line segment CQ, that's equals to 15 units in its length. In the next step, we'll join points Q and A together by a straight line. We join points Q and A together by a straight line. So in the drawing, we have peripheral angle QBA. This is peripheral angle QBA. Peripheral angle QBA is equal to 90 degrees in its size according to what is given as the question, and peripheral angle QBA subtend on chord QA. Again, peripheral angle QBA subtend on chord QA. So here we can implement rule 5. I'll repeat quickly on rule 5. According to rule 5, any peripheral angle that is equal to 90 degrees in its size must subtend on the diameter of the circle. In the drawing, we have a circle. This is peripheral angle MAN. This is equal to 90 degrees in its size, and therefore, according to this rule 5, peripheral angle MAN must subtend on the diameter of the circle. Peripheral angle MAN subtend on MN, that is the diameter of the circle. So according to this rule 5, any peripheral angle that is equal to 90 degrees in its size must subtend on the diameter of the circle. We can definitely implement rule 5 in our drawing. Why? Because in our drawing we have peripheral angle QBA that is equal to 90 degrees in size, and therefore according to rule 5, peripheral angle QBA must subtend on the diameter of the circle. Peripheral angle QBA subtend on chord QA, and therefore according to rule 5, QA must be the diameter of the circle. So I write it down. If you found out that chord QA is the diameter of the circle according to rule 5. We know that the diameter of any circle is twice as long as the radius. So if we define the radius of this circle as r, then the diameter must be equal to 2r. So QA equals to 2r. The diameter QA is equal to 2r units in its length. In the next step, I'll copy the right big triangle ABQ in a new page, and we will implement the Pythagorean on this right big triangle ABQ. Side BQ equals to 6 plus 15, that is 21. Side BA equals to 13 units in its length according to what is given as the question, and the hypotenuse AQ is equal to 2r. It is also the radius of the circle. Here by PT is the abbreviation for Pythagoras theorem. So actually, this is the right triangle QBA that according from the original drawing. In this right triangle QBA, according to the Pythagoras theorem, QA squared, that is the square of the hypotenuse, equals to QB squared plus BA squared. So I write it down. QA squared, that is the square of the hypotenuse, equals to QB squared plus BA squared. QA is 2r, therefore QA squared is 2r squared, that is 4r squared. And it is equals to QB squared. QB is 21, therefore QB squared is 21 squared, that is 441 plus BA squared. BA is 13, therefore BA squared is 13 squared, that is 169. So in total, if you found out that 4r squared equals to 441 plus 169. So 4r squared equals to 441 plus 169 is 610. So in total, if you found out that 4r squared equals to 610, here we divide this equation by 4, and we get that r squared equals to 610 over 4 is 152.5. In total, if you found out that r squared equals to 152.5. Our task is to find out the area of this circle. Actually, we know that the area of any circle is equal to pi times the radius of the circle squared. Okay, again, the area of any circle is equal to pi times the radius of the circle squared. And therefore, the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle squared is r square. So the area of our circle is pi r square. But r square is 152.5. So we substitute r square in this expression by 152.5. And we get that the area that we are looking for in this question, that is the area of this circle, is equal to either 152.5 pi square units in its size, or in terms of numbers, the value of this expression is equal to 700 479.09 square units in its size. But again, we should find out that the area that we are looking for this question, that is the area of this circle, it is equal to either 152.5 pi square units in size, or in terms of numbers, the area of this circle is equal to 479.09 square units in its size. So we finished with the first method. In the next step, I will present to you how to find out the area of this circle according to the second method. In the second method, we can use with the things that we already found out in the second method. In the first method, we have already found out that this is 97TC, this equals to 5 units in step. This is 97CQ, this equals to 15 units in step. So we use those two things in the second method. So in the drawing, we have chord BQ that intersects with chord TD at 90 degrees at point C. Again, we have chord BQ that intersects with chord TD at 90 degrees at point C. And whenever you have two chords that intersect with each other at a right angle at 90 degrees, that is to say, if in the intersection point they create between them 90 degrees, you can implement rule 26. Again, whenever you have two chords that intersect with each other at 90 degrees, you can implement rule 26. So I'll repeat quickly rule 26. First of all, rule 26 is true in any circle. So in any circle, if two chords, chord AB and chord CD, intersects with each other at a right angle, that is to say, at their intersection point, that is point O, they create between them, they create with each other 90 degrees. This angle equals to 90 degrees. So if two chords intersect with each other at 90 degrees, at point O, then the following equation is true. That AO square plus OB square plus CO square plus OD square equals to 4R square. And R is the radius of the circle. It's the radius of this circle. Again, when two chords intersect with each other at a right angle, that is to say, at the intersection point they create between them 90 degrees, then the following equation is true. That AO square plus OB square plus CO square plus OD square equals to 4R square. And R is the radius of this circle. So we can implement rule 26 in our drawing. Or because in our drawing, as I mentioned before, chord BQ intersects with chord TD at 90 degrees at point C. And again, chord BQ intersects with chord TD at 90 degrees. This angle equals to 90 degrees. They create between them at the intersection point that is point C 90 degrees with each other. So all the requirements of rule 26 are satisfied, and therefore we can implement rule 26. So I write it down. In our original drawing, we have chord BQ this is chord BQ intersects with chord TD and at the intersection point that is point C, they create between them 90 degrees. This angle equals to 90 degrees. So repeat again. In our original drawing, we have chord BQ that intersects with chord TD at 90 degrees, and the intersection point occurs at point C. So all the requirements of rule 26 are satisfied, and therefore we can implement here rule 26. According to rule 26, the following equation is true. That TC square plus CD square plus BC square plus CQ square equals to 4R square. And R is the radius of this circle. So I write it down. According to rule 26, the following equation is true. That TC square plus CD squared plus BC squared plus CQ squared equals to 4R squared. R is the radius of this circle. Repeat again, according to Rule 26, the following equation is true. TC squared plus CD squared plus BC squared plus CQ squared equals to 4R squared. This equation is the implementation of Rule 26 in our drawing. TC is 5, therefore TC squared is 5 squared, this is 25, plus CD squared. CD is 18, therefore CD squared is 18 squared, this is 324, plus BC squared. BC is 6, therefore BC squared is 6 squared, that is 36. Plus CQ squared. CQ is 15, therefore CQ squared is 15 squared, that is 225. And it is equals to 4R squared. So in total, if you found out that 25 plus 324 plus 36 plus 225 equals to 4R squared. 25 plus 225 is 250. And 324 plus 36 is 360. So in total, if you found out that 250 plus 360 is equal to 4R squared. 250 plus 360 is 610, so 610 equals to 4R squared. Here we will divide this equation by 4, and we get that R squared equals to 610 over 4 is 152.5. So if you found out that R squared equals to 152.5, our task is to find out the area of this circle. Actually, we know that the area of any circle is equal to pi times the radius of the circle squared. Therefore, the area of our circle must be equal to pi times the radius of our circle squared. But we already found out that the radius of our circle squared is R squared. So the area of our circle must be equal to pi R squared. So it is pi times R squared. But we already found out that R squared equals to 152.5. Therefore, we solve R squared in this expression by 152.5. And in total, we get that the area of our circle must be equal to either 152.5 pi square units in size, or in terms of numbers, this expression pi times 52.5 equals to 479.09 square units in its size. So actually, in both methods, we arrive to the same result. We should find out that the area of this circle in both methods, it is equal to either 152.5 pi square units in its size. In terms of numbers, the area of this circle is equal to 479.09 square units in its size. So we finish with the second method and the second question. So the next step, I will summarize the lecture. I'll start with the first question, of course. the first question, our task was to find out the radius of this circle. In the drawing, we have a circle. This is the right angle ABC. This angle ABC equals to 90 degrees in size. AB, side AB of triangle ABC equals to 4 units in its length. This is line segment AD. This is also equals to 4 units in its length. This is the short line segment DC. This equals to 1 unit in its length. Again, our task is to find out the radius of this circle. And we also know that this is point O, that is the center of this circle. Again, our task is to find out the radius of this circle. So first of all, we implemented rule 25 in our drawing. Actually, rule 25 is also defined as second tangent second theorem. According to rule 25, if from a common external point P, you will draw a tangent PA, and a line segment PC is defined also as second PC. Second PC cuts the circle at 2 points B and C. So from the common external point P, we have tangent PA that is tangent to this circle at point A, and we also have second PC that is cuts the circle at 2 points B and C. So in this drawing, the following equation is true, that PA square equals to PB times PC. Again, PA square equals to PB times C. So we can actually implement rule 25 in our drawing. Why? Because in our drawing, from the common external point C, we have tangent CE that is tangent to this second point E, and we also have second CA that cuts the circle 2 points D and A. So all the requirements of rule 25 are satisfied, and therefore we can implement rule 25 in our drawing. According to rule 25, the following equation is true, that CE square equals to CD times CA. Again, CD square equals to CD times CA. So again, according to rule 25, if you focus on this common external point C, the following equation will be true, that CE square equals to CD times CA. Again, CE square equals to CD times CA, according to rule 25. CE is the missing sign, so it is equals to CD. CD is 1 times CA. CA in total equals to 1 plus 3, that is 4. So in total we found out that CE square equals to 1 times 4, that is 4. So CE square equals to 4. Here we took a root of this equation and found out that CE equals to the square root of 4, that is 2. Okay. This is tangent CE that equals to 2 units in its length. In the next step, I copied the right big triangle ABC in a new French, and we implemented the Pythagoras theorem on this right big triangle ABC. The hypotenuse AC equals to 1 plus 3, that is 4, and AB equals to 4 units in its length, according to what is given the question. Okay, this is the right triangle ABC, that according to the original drawing, this right triangle ABC, according to the Pythagoras theorem, AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. AC is 4, therefore AC squared is 4 squared, that is 16, and it is equals to AB squared. AB is 3, therefore AB squared is 3 squared, that is 9, plus BC squared. BC is the missing sign, so it is. So in total, we should find out that 16 equals to 9 plus BC squared. Here we subtracted 9 from this equation, and finally found out that 16 minus 9 is 7, so 7 equals to BC squared. Here we took out of this equation, and found out that the missing sign BC is equal to the square root of 7 units in its length. This is the missing side BC that equals to the square root of 7 units in its length. Okay. In the next step, so what is the length of this missing line segment BE? BE equals to BC minus CC. BE equals to BC minus CC. So BE equals to BC. BC is square root of 7. Minus EC is 2. So in total, BE equals to the square root of 2, BE equals to the square root of 7 minus 2 units in its length. In the next step, we join points O and E together by straight line. Point O is the center of this circle, point E is the point of the circle itself, therefore OE is the radius of this circle. We define the radius of this circle as such, so OE equals to R. The radius of OE is equals to R, the radius of OE is drawn to point E, that is the point of tendency of tangent BC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius EO. If BC is perpendicular to EO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to all 1. In the next step, we did another construction. That is to say, from this point O, that is the center of the circle, we do perpendicular on AB. Again, from point O, we do perpendicular on AB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AB. This point is point L. By doing this construction, quadrilateral LOEB. Inside quadrilateral LOEB, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4 pieces again, in total must be equal to 360 degrees. According to the rule, that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this 4 pieces again must be equal to 90 degrees in size. So in quadrilateral LOEB we have 4 right angles. Therefore, according to all 5, quadrilateral LOEB is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So an rectangle LOEB side OE must be equal to the opposite side LB. But OE is up, therefore the opposite side LB, the opposite side LB must be also equal to R units in its length. Likewise, according to the sum rule, in the seventh again LOEB, side EB must be equal to the opposite side OL, but BE is square root of 7 minus 2, therefore the opposite side OL must be also equal to the square root of 7 minus 2 units in its length. So what is the length of this BC 97 AL? AL equals to AB minus LB. Repeat again. AL equals to AB minus LB. So AL equals to AB, AB is 3 according to what is the equation, minus LB, LB is R. So in total, AL equals to 3 minus R. In the next step, we join points O and A together by straight line. Point O is the center of the circle, point A is the point of the circle itself, therefore OA is the radius of this circle, that is equal to R according to our definition. In the next step, I copied the right green triangle ALO in a new page and we implemented the parallel on this right green triangle ALO. Side AL equals to 3 minus 1, side AL equals to 3 minus 1, side LO equals to the square root of 7 minus 2, and the hypotenuse AO equals to R. So actually, this is the right green triangle ALO, this is a copy of the original drawing. This right triangle AO squared, that is the square of the hypotenuse, equals to AL squared plus LO squared. AO is R, therefore AO squared is R squared, and this equals to AL squared. AL is 3 minus R, therefore AL squared is 3 minus R squared plus LO squared. LO is square root of 7 minus 2, therefore LO squared is square root of 7 minus 2 squared. So in total, we found out that R squared equals to 3 minus R squared plus square root of 7 minus 2 squared. So R squared equals to 3 minus R squared. 3 minus R squared equals to 3 squared, it is 9, plus R squared minus 2 times 3 times R, that is minus 6R, plus square root of 7 minus 2 squared. Square root of 7 minus 2 squared equals to 0.417. So in total, we found out that R squared equals to 9 plus R squared minus 6R plus 0.417. We have R squared on both sides of this equation, so R squared will get cancelled. After cancelled R squared, this side of this equation we left with nothing, that is to say 0, while on the other side of this equation we have 9 plus 0.417, that is 9.417 minus 6R. So in total, we found out that 0 equals to 9.417 minus 6R. Here we added 6R to this equation, and finally found out that 6R equals to 9.417. Here we divided this equation by 6 and finally found out that R, that is the radius that we are looking for this equation, is equal to 1.57 units in itself. Because again, if you hold on the radius r of this circle is equal to 1.57 units in itself. We finish with the first question. In the next step, I presented to you the second question, and we solved the second question in two different methods. In the second question, our task is to find out the area of the circle. So, in the drawing, we have a circle. This is line segment BC, this equals to 6 units in itself. This is line segment BA, this equals to 14 units in itself. Or chord BA equals to 15 units in itself. This is line segment CD, this equals to 18 units in itself. Those two angles are both right angles. Again, our task is to find out the area of this circle. So, first of all, those two right angles are defined as one-sided interangles. The sum of those two angles is, of course, 180 degrees. And according to Rule 27, if the sum of two one-sided interangles is equal to 180 degrees, then they must be located between parallel lines. The sum of those two one-sided interangles is equal to 180 degrees, and therefore, according to Rule 27, they must be located between two parallel lines. That is to say, BA is parallel to CD. Repeat again, according to Rule 27, chord BA is parallel to line segment CD. So, in the first step, in the next step, we define the center of this circle. This point is point O. And from point O, we do perpendicular on CD. Again, from point O, we do perpendicular on CD. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O in line segment CD. This point is point M. In the next step, we extended the perpendicular OM by side line until it touches chord BA. We define the touching point of the extended perpendicular OM with chord BA. This point is point M. We know that CD is parallel to BA, and therefore the perpendicular to CD must be also perpendicular to BA. Why? Explain why. Because if we have those two lines that are parallel to each other, that is to say line A is parallel to line B, and from this point we will go perpendicular to line A. The extended perpendicular will be also perpendicular to line B. Therefore, the extended perpendicular OM to line segment CD must be also parallel to chord BA. Okay, because those two lines are parallel to each other. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to what I've already explained. So here we have quadrangle BCMN. In quadrangle BCMN, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4-piece angle. In total, they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. And therefore, this 4-piece angle must be equal to 90 degrees in its size. So in quadrangle BCMN, we have 4 right angles, and therefore, according to Rule 5, quadrangle BCMN is a rectangle. We know that ON is perpendicular, so ON is a perpendicular, it is absolutely a straight line. Okay, again, ON is a perpendicular, it is absolutely a straight line. So if we focus on the lower side of the straight line ON at point M, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles from one side of a straight line is equal to 180 degrees. So which angles we have at the lower side of the straight line or end at point M? We have this angle that is the right angle according to our construction, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we did the construction. That is to say, from point A, we do perpendicular on CD. Again, from point A, we do perpendicular on CD. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and CD. This point is point L. By doing this construction, we created the lower quadrilateral MNAL. In the lower quadrilateral MNAL, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4 missing angle, in total it must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this 4 missing angle must be equal to 90 degrees in its size. So in quadrilateral NMLA we have 4 right angles, therefore according to rule 5, quadrilateral MNLA is a rectangle. So in conclusion, we have found out that those two quadrilaterals, they are all rectangles. They are both rectangles. Okay. So from the center of this circle, that is to say from point O, we have perpendicular ON on chord BA. From point O, that is the center of the circle, we have perpendicular ON on chord BA. And according to rule 19, the perpendicular from the center of the circle towards any chord bisects the chord. So the perpendicular ON to chord BA bisects chord BA. ON bisects chord BA. That is to say, it divides chord BA into two halves. The first half is BN, and the second half is NA. BA, chord BA in total equals to 13, so the first half must be equal to 13 over 2, that is 6.5, and the second half NA must be also equal to 13 over 2, that is 6.5. So if you know that BN equals to 6.5 and NA also equals to 6.5 units in its length according to rule 19. BC and M is a rectangle, and we know that the opposite sides of a rectangle are equal to each other. So a rectangle BC and M, side BN equals to the opposite side CM, but BN is 6.5, therefore the opposite side CM must be also equal to 6.5 units in its length. Likewise, NMAL is a rectangle, and we know that the opposite sides of a rectangle are equal to each other. So a rectangle NMAL, side NA equals to the opposite side ML, but NA is 6.5, therefore the opposite side ML must be also equal to 6.5 units in its length. What is the length of this missing line segment LD? LD equals to CD minus CL. Again, CD minus CL equals to LD. And again, LD equals to CD minus CL. So LD equals to CD. CD is 18 minus CL. CL is 6.5 plus 6.5, that is 13. So in total, LD equals to 18 minus 14, that is 5. So LD equals to 5 units in its length. In the next step, we extended line 7DC by straight line until it touches the circle. We define the touching point of the extended line 7DC with this circle. This point is point T. By doing this construction, we created it called TD. We can implement on chord TD rule 19 again, because we have from the center of this circle, that is to say from point O, we have perpendicular OM on chord TD. And according to rule 19, perpendicular OM from the center of the circle to chord TD bisect chord TD. That is to say, TM equals to MD. And again, according to rule 19, TM equals to MD. TM equals to MD. But MD in total equals to 6.5 plus 5, that is 11.5. So we can write here that MD equals to 11.5, and from this equation TM equals to MD equals to 11.5, we will derive that TM also equals to 11.5 units in its length. So from one side TM equals to 11.5, but from the other side TM also equals to TC plus CM. So from the other side Tm also equals to Tc plus Cm. From this equation, we will write that 11.5 equals to Tc plus Cm. Tc is the missing side, so we leave Tc it is, and Cm is 6.5. So we substitute Cm by 6.5. In total, we should find out that 11.5 equals to Tc plus 6.5. Here we subtracted 6.5 from this equation, and we found out that Tc equals to 11.5 minus 6.5 is 5. This is the missing answer at Tc. This equals to 5 units in its length. In the next step, we extended 97 BC by sideline until it touches the circle. We define the touching point of the extended 97 BC with this circle. This point is point Q. By doing this construction, we get another called BQ. Intersects with called TD at point C. Again, called BQ intersects with called TD at point C. And again, called BQ intersects with called TD at point C. So all the requirements of rule 15 are satisfied, and therefore we can implement the rule 15. According to rule 15, the following equation is true that TC times CD equals to BC times CQ. Again, TC times CD equals to BC times CQ. Read again the following, according to rule 15, the following equation is true that TC times CD equals to BC times CQ. TC is 5, CD is 18, BC is 6, and CQ is the missing side. So total we should find out that 5 times 18 equals to 6 CQ. Here we divided this equation by 6 and found out the missing side CQ equals to 18 over 6 is 3, and 3 times 5 is 15. So CQ equals to 15 units in its length. In the next step, we join points Q and A together by straight line. So in the drawing, we have triangle QBA. This is equal to 90 degrees in size according to what is given in the question. The triangle QBA subtend on chord QA. And according to rule 5, any triangle is equal to 90 degrees in size must subtend on the diameter of the circle. Triangle QBA, this triangle QBA equals to 90 degrees in size, and therefore it must subtend on the diameter of the circle. Triangle QBA subtend on chord QA, and therefore according to rule 5, chord QA is the diameter of the circle. QA is the diameter. QA is twice, the diameter of any circle is twice as long as the radius. So if the radius is R, then the diameter of QA must be equal to 2R. In the next step, I call it the right triangle QBA. In the new page, and implemented the bottom also on this right triangle QBA. QB in total equals to 5 plus to 6 plus 15, that is 21. BA equals to 14, and the hypotenuse QA equals to 2R. Okay, this is the right triangle QBA, that is according to the original drawing. In this right triangle QBA, according to the bottom drawing, QA squared, that is the square of the hypotenuse, equals to QB squared plus BA squared. QA is 2R, therefore QA squared is 2R squared, that is 4R squared. And it is equals to QB squared. QB is 21, therefore QB squared is 21 squared, that is 421. This is 441 plus BA squared. BA is 14, therefore BA squared is 14 squared, that is 169. So in total, we found out that 4R squared equals to 441 plus 169. 441 plus 169 is 610. So 4R squared equals to 610. Here we divided this equation by 4 and found out that R squared equals to 152.5. Our test is to find out the area of this circle. Actually, we know the area of any circle is equal to pi times the radius of the circle squared. And therefore, the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle squared is R squared. So the area of our circle must be equal to pi R squared. But R squared is 152.5, so we substitute R squared by 152.5. And finally found out that the area of this circle, that is the area that we are looking for this question. It is equal to either 152.5 pi square units in size. In terms of numbers, the area of this circle is equal to 479.09 square units in its size. So we finish with the first method. In the next step, I present it to you how to find out the area of this circle according to the second method. in the second method, we use the things that we already found in the first method. We already found out in the first method that this is line segment CQ is equals to 15 units in length, and this is the short line segment TC is equals to 5 units in length. So we use those two things that we already found out in the first method and the second method. So in the second method, we use here rule 26. Whenever you have two chords that intersect with each other at a right angle, you can implement rule 26. In our drawing, we have chord TD, it intersects with chord QB at 90 degrees at point C. Again, we have chord QB, it intersects with chord QB intersects with chord TD at 90 degrees. At their intersection point, that is to say at point C, they create between them 90 degrees. So therefore we can implement here rule 26. And please click on rule 26. According to rule 26, rule 26 is shown in any circle. In any circle, if chord AB intersects with chord CD at point O at 90 degrees, at their intersection point, that is to say from point O, they create with each other 90 degrees. So in this moment, the following equation is true that AO square plus OB square plus CO square plus OD square equals to 4R square, and R is the radius of the circle. So we can implement rule 26 in our drawing. Why? Because in our drawing, as I already mentioned before, chord TD intersects with chord BQ at point C at 90 degrees. So all the requirements for rule 26 are satisfied, and therefore we can implement here rule 26. And again, in our original drawing, we have chord BQ that intersects with chord TD at 90 degrees at point C. Therefore, according to rule 26, we get that TC square plus CD square plus BC square plus CQ square equals to 4R square. Okay, again, according to rule 26, the following equation is true that TC square plus CD square plus BC square plus CQ square equals to 4R square. Again, R is the radius of the circle. TC is 5, therefore TC square is 5 squared, that is 25, plus CD square. CD is 18, therefore CD square is 18 squared, that is 324, plus BC square. BC is 6, therefore BC square is 6 squared, that is 36, plus CQ square. CQ is 15, therefore CQ square is 15 squared, that is 425, and this equals to 4R square. 25 plus 425 is 450, and 324 plus 36 is 360. So total, if you found out that 250 plus 360 equals to 4R square. 450 plus 460 is 610, so 610 equals to 4R square. Here we divided this equation by 4, and we found out that R square equals to 610 over 4 is 152.5. Our task is to find out the area of the circle. If you remember that the area of any circle equals to pi times the radius of the circle squared. And therefore the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle squared is R square. So the area of our circle must be equal to pi R square. But we already found out that R square equals to 152.5. So we substitute R square here by 152.5, and finally found out that the area of our circle is equal to either 152.5 pi square units in size, or in terms of numbers, the area of this circle is equal to 479.09 square units in its size. So in both methods, we arrive to the same results. Okay, thank you very much.